So we'll talk a lot more about bond energies when we get into our thermodynamics section, but in the meantime, we will want to talk about bond energies as far as trends go. And this is important when we're talking about chemical bonds, because in chemical reactions, we're going to break bonds from our reactants, and then we're going to make new bonds or form new bonds for when we form product. And we can estimate our reaction energy by thinking about how much energy it takes to break a bond, and then how much energy is going to come out when we get new bonds. And so this bond energy is how much energy it takes to break 1 mole of a bond, of a compound. So in general, the more electrons that are shared, the higher or the stronger the bond is. So we can compare different atoms that are connected. So carbon-carbon bond, you can see single bond is 350-ish kilojoules, a double bond 600, a triple bond 840-ish. And so you can see that as we increase the number of bonds that are shared, or electrons shared, it's getting stronger. And that goes with carbon and nitrogen as well. This also, so that's bonding, so there's one way. And then another way is we can compare different sizes. So in general, the shorter the covalent bond is, the stronger the bond. So remember, when we have the energy is proportional, and I'll do proportional to the charges of each divided by the radius squared. So if we have atoms that are smaller than their radius, so that distance between the two atoms is going to be shorter, which means that the energy will be bigger. So bonds are going to get weaker as you go down the column, or less strong, because your distance is getting bigger, so your energy is going down, and they're going to get stronger as you go across, because your radius is getting smaller, so your energy is going to go up. So also, bonds depend not only on the connection, but the other atoms that are around it and the other factors. So what phase are we in, stuff like that. So what we want to do is predict it in the gas. We do this in the gas state, so we're getting as close to an isolated system as possible, and we're going to use the average of all the bond energies, so all the methods we form. In general, well, always, bond breaking is endothermic. It's always going to require energy. It's going to be positive. Bond forming is exothermic. We're always going to be releasing energy, so delta H of forming new bonds is going to be negative. And then our enthalpy of reaction, we're going to add up all of the bonds we break, which is a positive number, and we're going to add that to all the bonds we form, which will be a negative number. And so that will tell us whether our reaction is endo or exothermic. It'll help us predict. Again, more electrons that are shared, the stronger the bond. So we would think that, if we share 2 electrons to have a single bond, it should be about half as strong as sharing 4 electrons. But what actually happens is a double bond is less than twice as strong. So we're going to need a different theory to help us to understand what's going on here. And then in general, bond strength is related to that bond energy, but it's the energy it takes to break the bond completely in half. And we talked about that we know that the more electrons we share, the higher the energy. We also know that the closer they are, the stronger the energy. So if we put those two together, then we can predict that the more electrons that they share, the shorter the bond as well. So bond length is measured between the distance between the nuclei of the two atoms. In general, triple bonds are shorter than double bonds, which are shorter than single bonds. And we can see that here with carbon. As we start to share more electrons, it gets smaller. And generally, our bond length, again, is going to decrease as we go from left to right due to effective nuclear charge. And the bond length is going to increase as we go down because we're having higher energy level. So we can see that here. So now we're going to get into this next theory, which will help us to talk about some of those bond energies while we're transitioning. So VSEPR theory helps us to predict the structure of compounds, which will help us to determine their properties, because remember, structure is related to properties. So the issue currently is that Lewis structure is limited to 2D space, and we know that molecules are 3 dimensions, or living in 3 dimensions. So this structure is going to relate to how are they arranged, the kinds of bonding we have going on, do we have ionic, covalent, polar covalent, and then therefore the shape of the molecule. So we're going to use Lewis theory to help us move past that into VSEPR theory. Because we're dealing in 3Ds, we're going to have 3-dimensional geometries, and they'll be related to geometric figures. And so each of these figures will have angles between the bonds in the molecule. So first thing we're going to talk about getting into this is electron groups. So there are regions of electron groups that are in every atom. This could be connections from one atom to another with electrons, so bonds, or it could be a lone pair. So we know that electron groups should repel each other because they are all negatively charged. And so what we can do here is to think about how many electron groups there are on a central atom, and then use that to think what kind of shape is going to be formed to minimize repulsions. So we'll be thinking about the position of the atoms around the central atom with relationship to bonding and non-bonding electron groups, and we're going to minimize the repulsion by maximizing their separation. So electron groups are going to be most stable when they can get as far apart as possible. So that's the basis of VSEPR theory, which is valence, shell, electron, pair, repulsion. So the valence shell, so the electron pairs in the valence shell repelling each other. Because they're negative part, they're going to be separated as much as possible. And then we can count how many electron groups there are, and we can predict what the shape and the bond angles are going to be. So we're going to use the Lewis structure. So everything we've done so far, we're still going to do it. We're going to use the Lewis structure and count how many valence electron pairs are on the central atom. We're going to count every lone pair and every type of bond. So it doesn't matter what kind of bond, so bond type doesn't matter. We're just going to count the bonds. So if I have nitrite, NO2, I'm going to do that Lewis structure. So 5 valence electrons from nitrogen, 12 from the oxygen, and 1 from the negative charge. That will give me 18. So if I do N, O, 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, nitrogen's missing an octet, so I will get rid of those and add a double bond. Okay, so for nitrite, we're going to have, so let's think about how many connections I have. I have this connection here, this connection here, and then this pair, lone pair. So when I draw this, I have one lone pair, I have one single bond, and I have one double bond. So I have two types of bonds and one lone pair, so there are 3 electron groups. I like to just think how many things are around it. So I have 2 atoms and one lone pair. Based on this, there are 5 basic electronic geometries that we're going to learn: linear, trigonoplanar, tetrahedral, trigonal, bipyramidal, and octahedral, corresponding to 2 electron groups, 3, 4, 5, and 6. And each of these electron geometries are going to have different molecular geometries depending on how many of these electron groups are atoms versus lone pairs. So, and in general, when we have resonance structures, it shouldn't matter which one you use because the geometry should still be the same. The electron group shouldn't change. So when we have 2 electron groups, this is called linear. In this case, they're going to be, the maximum amount of separation is going to make it 180 degrees from each other. So linear geometry. So beryllium chloride here has 2 connections, 1, 2 atoms, and so 180. Carbon dioxide only has 2 atoms on it, so linear geometry. 3 electron groups is called trigonal planar. When we look at this, so this is when we have 3 electron groups, the maximum separation is 120 degrees. So we can see if we connected these atoms, it looks like a triangle, and it's in one plane. So trigonal planar geometry. 4 electron groups is called tetrahedral. So this is where we start to break into 3 dimensions. The other 2 are still kind of in that 2D, 1D space. So tetrahedral geometry, when we have 4 electron groups, then when we draw it on paper, it looks like the angle should be 90, but when we are able to spread out into 3D space, they're able to separate more, so the bond angle is 109.5. So the only one with the decimal that you have to remember. 5 electron groups is called trigonal bipyramidal. In this case, there are 2 different types of electrons for trigonal bipyramidal. So it's called trigonal bipyramidal because basically we have these 3 atoms on this center part along this equator. We call those the equatorial positions, and they look like a triangle if we were to look at them from the top, and they have an angle of 120 degrees from each other. So that's why we call it trigonal. And then it looks like if we looked at these carbon or these chlorines here, if we were to look at it from the top, it kind of looks like a pyramid. And we have that on top and on bottom, so that's where the bipyramidal part comes in. And the angles on this equatorial part, that is, so those, around the base, these are the equatorial positions, and the angle is 120 degrees between those atoms. And on this, between the top and bottom part, that is called the axial position, and those bond angles are 90 degrees from the top to the equatorial position. The last electronic geometry we're going to learn about is octahedral. And this is when there are 6 electron groups along the central atom. And in this case, we have like a square base, and one up top and one down below. And these are completely symmetric with 90 degrees between any bond angle. So when we have 6 things, that is octahedral. And this question is asking, why do we only consider electron groups around the central atom? And so keep in mind, on our terminal atoms, we do have electron pairs, but they happen to be so far away from the central atom that they're not going to impact the repulsion, and so they won't really impact the geometry much. For HCN, here's the Lewis structure. So we're going to figure out the geometry. So there's 2 groups. So when there's 2 groups, that's called linear. Let's determine the molecular geometry of nitrate and then carbon tetrachloride. So first we need to draw the Lewis structure. We're going to count valence electrons. So we have 24 valence for nitrate. So we'll draw the Lewis structure. Skeletal structure first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, nitrogen doesn't have an octet, so let's get rid of one of those lone pairs and make it a bond. Okay, here's nitrate. So it has 1, 2, 3 things around it, so that is called trigonal planar because there are 3 electron groups. Okay, carbon tetrachloride, we have 4 plus 4 times 7, so that equals 32. So we're going to have carbon, 4 chlorines, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So already filled. Everybody's good. 1, 2, 3, 4 electron groups. So 4 electron groups means tetrahedral. Okay, so when we start to think about how many atoms are attached versus how many electron groups are attached, we're going to get subsets of the geometry or the shape of what the atoms are doing. So this is where the actual geometry, or what we'll call the molecular geometry, will be different from the electron geometry. In electron geometry, we're just thinking about what kind of electron groups are attached and how many electrons are, how the electron groups are affecting the geometry. But when we think of what the atom looks like in terms of the atoms attached, that's going to be what we call the molecular geometry. So keep in mind the lone pairs are going to affect geometry since we're going to take up space, but they're not seen in the sense that they're not actual matter. Well, they're not as much matter as an atom, and so we're going to think about what the atoms are doing. So that when electrons are in lone pairs, they're not bound to another atom, so they're not localized, so they can actually take up more space than when the electron groups are in a bond. When we have a bonding pair, they're connected to another atom, so they're kind of localized, so they don't take up as much room. So repulsive force is biggest when it's a lone pair, then less repulsion when a bond is connected or is reacting or interacting with a lone pair, and then bonds are have the least amount of repulsion. Like I've been saying, the geometry is going to be a little different, the naming anyway, when we think about how the electrons are arranged, electron groups are arranged. That's called the electronic geometry. And when we just look at terminal atoms instead of lone pairs, that's going to be the molecular geometry, so it's like a subsect. So when we have trigonal planar geometry, when we switch one of the bonds to be a lone pair, that is called bent. So again, when we have 3 electron groups and one of them is a lone pair, meaning the other 2 are from bonds, this is a trigonal planar bent shape. And the bond angle is a little less than 120. Because of this, electron group is taking up a little more space than it would if it was a bond, squishing these angles a little bit more, or a little bit closer together, so it's less than 120. When we have tetrahedral geometry, we can either have trigonal pyramidal or bent geometry. So in the case where we have 3 bonds, and so 4 electron groups total, and one of them is a lone pair, meaning 3 of them are bonds, this is called pyramidal or trigonal pyramidal. Because we have a triangle base here, but it's not quite in a plane, so it kind of looks like a pyramid. So the electron geometry here is tetrahedral, but the molecular geometry is called pyramidal. And the bond angles then, since this lone pair takes up more space than if it was a bond, is a little less than 109.5. It's actually 107 degrees. When when we have, again, 4 electron groups and 2 are lone pairs, meaning 2 are bonds, this is called tetrahedral bent. We want to specify that it's tetrahedral because we have the trigonoplanar bent. It's in a plane. It looks similar to the trigonoplanar bent, but it has a smaller bond angle since there's 2 electron groups pushing them together. And the bond angle is less than 109.5, it's actually 104.5. So anytime there is another electron group, we are going to subtract about 2.5 degrees in the case of tetrahedral. So here we have tetrahedral is our electronic geometry, and our molecular geometry is bent. Now when we have 5 electron groups, the way that the atoms are going to come off and replace with electron or lone pairs is specific. So in order to have more space, because electrons want to have as much space as they can get for those repulsions, they're going to come off from the equatorial positions. And that's because between the axial and equatorial, there's only 90 degrees. And so that doesn't give it as much room. So when we come off from the equatorial position, now they have 120 degrees of space. So the equatorial is where those electron groups will replace the atoms. And so those equatorial bond angles are going to be less than 120 degrees, and then the bond angles between the axial and equatorial will be less than 90 degrees. And so when one group becomes a lone pair, this is called seesaw. Because if we were to tilt it on its side, it kind of looks like a little seesaw. So here we have the equatorial position. Here's 5 electron groups. That's called trigonal bipyramidal. And the molecular geometry is seesaw. When we take off 2 electron groups, so we have 2 lone pairs around the central atom, still trigonal bipyramidal, but now the geometry is going to look kind of like a T, so that's called T-shaped. And bond angles are going to be a little less than 120 or than 90 degrees here because they're going to be pushing, so a little less than 90 between those. And when there are 3 lone pairs around the central atom, this is called linear. So notice 3 lone pairs. It still looks electronically like 5 things are there, so it's trigonal bipyramidal. But the atoms, the terminal atoms that are left, makes it look like a line, so it's called linear. And that bond angle is 180 degrees. Lastly, when we have octahedral geometry, 6 electron groups. Since these are all equal, all the bonds are equivalent, it doesn't really matter which one comes off first. So we'll just take one off, and if you notice, it looks like a square here in the shape of a pyramid. So that's called square pyramidal. So one lone pair makes square pyramidal. And our bond angles end up being a little less than 120. When we have two lone pairs, that's called square planar. In order to give it the electron lone pair the most room, we'll have one come off the top and one come off the bottom, making these equivalently looking like a square. So octahedral electronic geometry still, since we have 6 electron groups, and square planar molecular geometry. Here's a little summary sheet that you should have in your notes. Okay, so how do we go from Lewis structure into molecular and electronic geometry? So first you're going to draw Lewis structures. Then you're going to figure out how many electron groups you have, so determine the number of electron groups. Then identify which ones are lone pairs or bonds and count each type. And remember, single, double, and triple bonds are still one group. And then use the table to help you figure out, or eventually use your mind. So let's do phosphorus trichloride and chloronitrite. Okay, so PCl3, we have 5 plus 3 times 7, so 26 electrons. So phosphorus and then chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Everybody has an octet. So we have 1, 2, 3, 4 electron groups. So that's going to be tetrahedral electronic geometry. And its molecular geometry will be, we have 3 bonds, so 3 atoms, and 1 lone pair. So that's trigonal, pyramidal. And the bond angle will be less than 109.5 degrees. For Cl and O, we have 7 plus 5 plus 6, so 18. So we're going to put them in that order. So 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14, 16, 18. Nitrogen does not have the lone pair, so we will, or an octet, so we'll remove one from oxygen and put it here. Now I know to remove it from oxygen because I know oxygen likes 2 bonds, and which gives it a formal charge of 0, having 2 bonds and 2 lone pairs, but you can try different ones, just remember formal charge. So in this case we have 1, 2, 3 groups. So that's the electronic geometry is trigonal planar. And because we have 2 groups, 2 atoms and 1 lone pair, then our molecular geometry is bent. So our bond angle is less than 120 degrees. For ICl4, we are going to have 7 plus 7 times 4 plus 1, so 36. So I have iodine, 4 chlorines, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So this is an expanded octet, and that works since it's in the below the 3rd row. So let's count groups. I have 1, 2, 3, 4 bonds, 5, 6 with lone pairs. So 6 groups. Electronic geometry is octahedral. Now octa means 8 and hedral means sides. And when we have an octahedral, it means even though we have 6 electron groups, we have, if we were to count how many faces or sides it has 8 sides if it was like a die. So molecular geometry, when we have 4 atoms, 2 lone pairs, that is square planar. And our angles are, angle is 90 degrees between the atoms. Now I3 minus, I have 7 times 3 plus 1, so 22. So iodine, 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 2, 4, 6, 8, 10, 10, 12, 14, 16, 18, 20, 22. So I have 1, 2, 3, 4, 5 groups. So 5 groups means trigonal bipyramidal for electronic geometry. And then molecular geometry, I have 2 atoms, 3 lone pairs, so that is linear. The bond angle is 180 degrees between each of those iodine atoms. So how do we draw these on paper? Well, you'll do a lot more of that if you take organic chemistry, but since we are dealing with paper, we have to try to figure out a way to make it look visually like 3 dimensions. So we put the central atom on the plane of the paper. Then you're going to try to put as many atoms as possible in the plane with a straight line. For atoms that are in front of the page, you'll use a solid wedge, such as this, where it's all filled in. For atoms that are behind the page, you're going to do a hatch, so something that looks like that, to try to make it look like it's behind. And if it's in the plane, it will just look like a straight line. So when we have 2D, like those 3 and this one, we get to, luckily, just use straight lines. When we start to get into 3 dimensions here and down here, then using those hatched and solid wedges try to give us some dimension. So in real life, we have many molecules have more than one central atom since they have a large structure. So when that happens, we are going to give each central atom, its own shape or own geometry. So how do you know if it's a central atom or not? Well, a central atom, a certain terminal atom is only connected to one other atom, so those will not have a geometry. So if we have 2 or more atoms or lone pairs, well, really just 2 or more atoms, then we'll have a different geometry. So here's glycine. It has 4 central atoms, so we're going to look at each one. So first off, the nitrogen. So it has 1, 2, 3, 4 groups, and of those groups, 3 of them are atoms. So it's tetrahedral, but 3 are atoms and 1 is a lone pair, so that is trigonal pyramidal. For carbon, it has 1, 2, 3, 4 atoms, and no lone pairs, so that is tetrahedral. This next carbon has 1, 2, 3 groups. All of them are atoms, no lone pairs, so that is trigonal planar. And this last oxygen here, now notice this oxygen has only 1 atom attached, so it's not going to have a geometry. But this one has 2 atoms, 2 lone pairs, so it's tetrahedral in electronic geometry. And since 2 of them are atoms and 2 are lone pairs, we'll call that bent. So we have trigonal pyramidal for our nitrogen, tetrahedral here, trigonal planar, and bent. So you can see that. So if I have methanol. I'm just going to draw it for you. We're going to predict the geometries. So we have CH3OH. You can check me. I know it's right. So for this carbon, we have 1, 2, 3, 4 things, 4 electron groups. All of them are atoms, so that's tetrahedral. Now in this oxygen, I have 1, 2, 3, 4. So tetrahedral electronic geometry, but 2 of them are atoms, so this one is bent. Tetrahedral bent. Here we have, I'm just going to draw these ones. Acetic acid looks like this. Okay, so for this carbon, we have 1, 2, 3, 4, all atoms, so tetrahedral. For this one, we have 1, 2, 3, so trigonal-planar, no lone pairs. And for this oxygen, 1, 2, 3, 4, so that's tetrahedral bent. Now in propane, we have C, 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 8 H's. This is the only way to draw it since the hydrogens are all terminal atoms. And notice each of these, 4, 4, 4, each of those are tetrahedral. Okay, now polarity in molecules. So we've learned about polar bonds, and polar bonds happen when we have a electronegativity difference in our 2 different atoms. And that's usually when it's greater than 0.4, and we can have that dipole. What also gives us polar bonds or polar molecule is if we have asymmetry in our shape. So basically, when we have these lone pairs, they're going to make a molecule be polar because they affect the symmetry. They make the molecule, the atoms that are attached, their dipoles not cancel out. So for example, here's hydrogen chloride, where we showed this earlier, a partial positive by the hydrogen, partial negative by the chlorine, because there's that electronegativity difference towards the chlorine. So that molecule is polar because there's going to be electrons pulled towards the chlorine end, because chlorine is more electronegative than hydrogen. So that gives us a polar molecule. So let's look at carbonite or carbon dioxide. So carbon dioxide, we've drawn it already, looks like this. It has a dipole pulling towards the oxygens, and because of that, they're pulled in opposite directions. So the bond between the carbon and the oxygen, that is a polar bond. But because they're both pulled towards the oxygen atoms equally in opposite directions, since the oxygens have the same electronegativity compared to carbon, then that's going to cancel out. So we got pull one way, pull the other way. They're the same sign and same magnitude, so they're going to cancel out. So our molecule will be nonpolar. Now, water looks like this. We have oxygen and hydrogen, and we have those 2 lone pairs. So when we draw it, it's a bent shape. So oxygen has that electronegativity difference here. So we are going to have polar bonds because the oxygen is going to pull equally because it's more electronegative than the hydrogen atoms. But the lone pairs here, mess up the symmetry. So they make it so that those dipoles do not cancel out. From those, so we end up getting a polar molecule. So I'm actually just gonna do a little aside here. So an aside, we can go through vector addition and all of that, but the general gist is if you have lone pairs on your atom or on your central atom, your molecule will be polar. Because the dipoles do not cancel out. Unless your molecule happens to be a symmetric molecule. So in that case, we'll have our octahedral square planar and our trigonal bipyramidal linear. In those cases, they have lone pairs on them, but their overall molecular geometries end up being symmetric, such that their dipoles will cancel out if the terminal atoms are the same. So these will be nonpolar if terminal atoms are the same element. And that's the case for all molecules that have no lone pairs. They're going to be nonpolar only if the atoms are the same element. So that's kind of the gist. If you have lone pairs on your central atom, they'll be polar unless they're octahedral and square planar or linear, and those terminal atoms are the same, then they'll be nonpolar. And everything that has only atoms and no lone pairs will be nonpolar, assuming the terminal atoms are the same element. So I'm going to not worry about these vector addition and all that stuff because ultimately, if you remember those other rules, that's really what should come in handy. So let's practice that. So NH3, we have 5 plus 3, so 8 valence. Okay, so that's what it looks like. It's trigonal, pyramidal, and tetrahedral electronic geometry. Since it has a lone pair, it's not one of those exceptions where square planar or linear, so this will be a polar molecule. CF4 has 28 plus 4, so 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So these have very polar bonds. Fluorine is pulling on these electrons in those bonds, but because there are no lone pairs on my carbon, those polar bonds will cancel out. So this is non-polar. Up here we have some just quick things, which we'll talk about in our solutions chapter, but in general, polarity is going to matter. Polar molecules are attracted to other polar molecules, and that's because they're basically like little magnets. So there's a partial positive, partial negative. So those charged sides are going to be attracted to other polar molecules, which makes polar molecules dissolve in water because water is very polar. It will also dissolve ionic compounds. Some molecules actually have polar and nonpolar parts. So soap has this nonpolar tail and a little polar head, which makes it very ideal when we have greasy hands. We could put soap on. The nonpolar tail will attach to the grease. We rinse with water. You have to rinse with water. So that way the water molecules will attach to the polar head and it can all go down the sink for us. This is the end of chapter 5, but don't forget all of this because we're going to build off of this into chapter 6.